Once again, welcome to the lecture on communication. We are now 16.3 in the syllabus, digital communication. Right? As this one tell you, this is analog signal. Variation of can be voltage, can be voice with time. This is the digital form, variation with time. This is from my notes. Okay, transmission of information by digital means. Right? What you speak, there's the information, there's a signal. The information carried in modern telecommunication system may be broadly categorized as audio, video, or data. So it doesn't have to be voice, audio, it can be picture and voice, or it can be what you do in an experiment you want to send to a friend. Right? It can be data. So that is your information, audio, video, data. That's your signal or information. And it enter a transducer, right? Basically, microphone change your speech, sound speech to alternating current equivalent to your sound speech. That's your transducer. And generates a signal voltage. So a microphone generates for you an alternating voltage that we call signal voltage. Okay? It's a transducer. Then what come out is your alternating voltage corresponding to the speech. Right? So we term the alternating current as the information signal. Right? Is equal to the speech that you speak. So it can be either analog or digital. What come out here, analog or digital. This is microphone, it will be analog. Okay, so this is analog signal. Basically, what's analog signal? It varies in time. It changes with time. Same as if it's a speech, the voltage varies as the speech changes. Right? That's your physical property of sound. Your speech changes, your voltage also changes. These signals are continuous in time. It doesn't stop. Right? Continuous value changes with time and can have any value. Any value. There is the lowest, that's the highest value. You can have any value there. No limit. Between the two limits, the lowest value and the highest value. Can have any value between that. Example of analog signal voltage generated by microphone. I speak, the microphone converted to alternating current. That is exactly the same as my speech. So in this topic, you will have to learn how to convert from analog to digital. Like 14, right? We'll go to learn it is 1110. A is 1000. Actually, it's 1000, not 1000. Right? It's binary. 10 is 1010. Okay, we have learned about electronic. So where we have the waveform coming out, going in very small. This is your operation amplifier. We send it to the positive. So it's a non-inverting voltage amplifier. So we amplify the amplitude only, not the frequency, just amplitude. So operation amplifier with negative feedback, that's your negative feedback, is another example of analog system. That's your digital signal, that's your voltage, that's your time. So this is 0, this is high. Digital signal consists of high, that's high, and that's low. high and low only, no other value. There's no intermediate value. Right? The low is 0, the high is 1. Right? Basically, it's a code representation of the original information. Right? Binary, then can break the code. If it's not binary, then to you it's just pulse only. Right? That can be 1, then 0, 0, and then 1, 1. Right? So it's 1, 0, 0, 1, 1. Right? There are many examples. Some of it will be stream of high and low voltage produced by digitized telephone call calculator. Right? Mass-produced calculator can use digital system. Advantage of digital energy transfer can be perfectly regenerated. That's one advantage. You reproduce it, you don't lose anything. In long distance travel, noise does not accumulate on the signal with repeated amplification. If it's analog, keep on picking up. We can reduce, we can filter it out, but it is still there. And every time we amplify, it becomes bigger and bigger. But not with digital. Right? We'll see in a while. Digital circuits are well suited for mass production. Right? We use gates so that can be mass produced. So if it can be mass produced, not individually produced, then it can be relatively inexpensive. Then you can add extra data to check or correct or transmitted signal. More reliable circuit. Large data carrying capacity because we are using infrared in optic fiber. The infrared higher frequency than radio wave. Right? So greater bandwidth. Attenuation and noise. If a signal is transmitted in digital form, then it also suffers attenuation. Energy is always lost as it travels from one place to another. And it will pick up noise somewhere. Right? Whether from an instrument or in the transmission process. So that's why it becomes smaller. Right? We call attenuation. Amplitude becomes smaller. And then the irregular checker make it not smooth there. That's the noise. And then when we pass it through the amplifier, we call it regenerator amplifier. We reproduce it. Okay, right? The original signal is reproduced. Right? No noise at all. Noise got whipped up. Perfectly regenerated. That's one thing we know. It's the same as the original signal. Okay? That's just a review. That's your comparator. 0. This can be 3 millivolt. Right? Or it can be 2 millivolt. It doesn't matter. But what comes out, because this is non-inverting, it comes out Vs. If your Vs is 5 volt, it could come 5 volt. The smaller fluctuation, like the noise here, it doesn't matter. It will not be amplified at all, because anything greater than 0 is amplified as Vs, the supply voltage. Powered amplifier that are used for amplifying digital signal are required only to produce a high voltage or low voltage. In this case, 5 volt. If this is 0, this is 0. That's all. High or low voltage. They are not required to amplify. This is not to amplify the noise. That's a right? Noise are small voltage fluctuation on the signal. Right? They are not required to amplify small fluctuation in amplitude. As the situation for amplification analog. Analog is different. Analog amplify the amplitude. So the noise also got amplified. Since noise consists typically of small fluctuation, right? Small changes on the voltage there, it's not amplified at all because this one just compare only. It doesn't matter whether it's 3 or whether it's 3 millivolt or 2 millivolt, give out a standard form, right? BS. The noise is not amplified. That's why we call it regenerator amplifier. And because they are able to reproduce the original signal, at the same time, filter out the noise. The noise is removed. No noise at all. Complete same signal as original when you send it to the regenerator amplifier. That's your analog signal. That's a noise. It's irregular. That's why it's not easy to remove because it's more like random. So it pick up signal plus noise. If the signal in the cable is analog, such as AM carrier with TV information or telephone information, the signal will pick up noise. That's your analog signal. It pick up noise. And when the signal is amplified, the noise has been amplified as well. It become bigger, the noise also get amplified. Because that's why it is amplifier. More fluctuation will be amplified. And as you go further, it got amplitude decreases again. You have to amplify it again. So the noise gets worse with amplification. Because you can do some filtering to minimize the cumulative effect of noise. I cannot remove completely. Right? So that's a fundamental problem with long distance analog transmission. They are noisy. Right? AM signal, turn on the AM radio, you will see it's a bit noisy. FM signal, FM radio, very clear, no noise. If, however, the signal in the cable is digital, such as modern digitized telephone information, right? Not like my time during the 60s there, I can hear the noise. Now, modern digital one, no noise at all. Then the signal before and after amplification can resemble the original. Right? We're just repeating, regenerated perfectly. So, pass through the amplifier, we call regenerator, comes out perfectly as like original. Digital pulses always have a standard rectangular shape. Noise can be completely removed from the input. The signal which has thus been regenerated. So digital signal can be preserved perfectly without any distortion from the influence of channel or noise. That's the advantage of digital signal. Analog to digital conversion. Okay, this one you need to know at least to about 30 or 40 conversion. Decimal to binary equals digital. It means the digital is in the form of binary, 1 and 0. In our familiar decimal system, we have symbols from 0, 1, 2, 3 until 9 to represent numbers. For example, we have 6 items, we write 6, but we have 10 items, then we have only up to 9 here. So we have to start another column, 1, 0. Right here, 1, 0, 1, that's your decimal, 2, 3, 4, and so on until we reach 9. So we come to 10, you have to write 0 and then start another column 1. Same, if it's binary, we start with 0 also. Each time we run out of symbol, we start a new column. Right? Same like 99. After that, 100. Start a new column. Right? Binary, we have 0. Then 1. No, we still have, we have 3 bit. Each is 1 bit. Each digit is 1 bit. We have 3 bit. Then the 0 is 0, the same. 0. Then after that, we finish already. We have 1. The others will be 0. Then we have normal already. Normal symbol already is 0 and 1. So the next step, we start a new column. 0 is 1 is 0. And then 3, we start the counting process is 0, 1, and then we just add 1 here. Right? And so on. So for 9, we have 1, 0, 0, 1. Okay, we learn in a while how to do the conversion. Decimal to binary equals digital. Any number written using decimal system is an array of digits corresponding to powers of 10. What does it mean? Example, you got 2,358. We write as 2358. 2 means it's 2 times 10 to the power 3. 3 means it's 3 times 10 to the power 2. That means it's 100. 5 is 5 times 10 to the power 1. 8 is 8 times 10 to the power 0. That means we start with 10 to the power 0, 10 to the power 1, 10 to the power 2, 10 to the power 3. And this is 2, 3, 5, 8. So 8 is what we call the least significant digit. 2 is the most significant digit. Two here is the most significant digit, and 8 is the least significant digit. LSD. Okay, so that's your decimal. We can convert to binary as we have just done that. Should be able to write all that. And then should be able to write the next one, 4. In binary system, we have two symbols only, 0 and 1. But otherwise, we count in exactly the same way. Then we just different symbol and then it's different. It's 2 is just 1, 0. 3 is just 1, 1. Thus, if we have one item, we write 1. But we have 2 items, then we write out of symbol. So we have to write as start new column 1, 0. So you should be able to complete that. Right? So 4 becomes your, then we have finished the symbol already, so we have to start a new column 1, 0, 0. 5, we can't start from here. 5, 0, 1. 6, right? Finish the 1. So we have to put 0 here and then 1 here. 1, 1, 0. 7 is all the 3, 1. Right? And each digit is called a bit. B-I-T. Right? Bit. Okay, so 111 means 3 bit. Thus, any number written using the binary system is an array of binary digit. Right? Bit stands for BIT, binary digit. Each binary digit is called bit. Right? And 1 here is 1 bit, 2 bit, 3 bit there. And each of them is to the powers of 2. That means this 2 to the power 0, 2 to the power 1, to the power 2. Example 43 items in decimal. How to write in binary? Right? We can write as 1, 0, 1, 0, 1, 1. Right? 1. Right? If we start from here, the least significant 1 times 10 to the power 0. That's another 1. and send to 2 to the power 1, and then 2 to the power 2, 2 to the power 2 is 0, 2 to the power 3 is 1, and then 2 to the power 4 is 0, 2 to the power 5 is 1, 2 to the power 5. Right? We can check. This 32, this one is 0, this one is 8, this one is 0, this one is 2, and that is 0. 2 to the power 0 is 1. 1 times 1 is 1. So we add up, it's 43. Right? One is your lead LSD. This one is your MSD. So we start with least is 2 to the power 0 and 2 to the power 1 to the power 2. Okay, just repeating. Left hand is the most significant bit. 1 is the least significant bit. Okay, you should be able to try to get all these numbers. They're done for you, 43. Right? So you can use that one to calculate out, or you can use calculator. Right? Just remember to press the mode twice to select the base. Then press 3, select the base, what base you want to use. Then press S square to select hexagonal or decimal. Press the number in decimal, right here. Press 13 in your calculator. And then press equal. And then press log to clear. Now you can try that. So the first one should be that. Okay, next one is 13. Right? 13 you can see is this one, 1, 8, this is 0, right? This is 8, sorry, this is 1, so 4 plus 8 is 12, then you want 1 here, 0 here. So this is about 25 is 16, plus 8 is 24, and plus 1. So it's 1, 1, 0, 0, 1. Right? 43, we just have done that. If you have the newer calculator, then it's slightly different. You have to press the mode once to select the base, press 4, select the base, and then press the number in decimal, whatever number you want. That means 25, press 25, then press equal. Save, press lock to clear. Okay, you need to know how to convert from binary to from decimal to binary and binary to decimal. Okay, there is various ways as I've shown you, calculator, work it out, or you can use this method. 13 divided by 2 is 6, remainder 1. 6 divided by 2 is 3, remainder 0. There's no carry forward, no remainder. 3 divided by 2 is 1 plus 1. Then you read from 1 from here. So it's 1, 1, 0, 1. That's the alternative way to do it if you prefer. Right? Some of you may have learned in your maths class. How to reproduce an analog signal after converting to digital. Right, let's go for a short break. Let's go for video.
Aliasing, the Nyquist theorem, these are all things that we've discussed here and there on this channel, but we've never once looked at, this subject as a whole. What we're going to do today is we're going to look at sampling. We're going to go from the ground up, and hopefully in doing so, well, all the other concepts will sort of come into place naturally instead of, being isolated videos like they used to be. So sampling is our topic of choice today. You're watching another Random Wednesday episode on 0612 TV. Hello and welcome to another Random Wednesday episode. So today we're going to take sampling from the ground up. And so let's begin by illustrating, the whole idea of why we even need sampling in the first place with a very simple example. Now, take for example, I'm just sitting here and I'm talking. Basically, what I'm doing is I'm generating these little compressions and rarefactions in air that an ear will pick up as sound. So essentially, sound is just movement of air. We can actually represent this in terms of a waveform. And a waveform will look something like this. And what this is trying to show you is that at a particular point in space, this is what's happening to the air particles in the area. They're moving back and forth over time. So you can imagine the vertical axis of the waveform basically telling you, how the air is moving either backwards or forwards with respect, of course, to a zero position. And the horizontal axis of this waveform represents time. So right, let's say now I'm talking and you want to record this. You want to capture this so you can play it back at a later time. Clearly, the way in which you want to do that is to basically record the movement of air over the duration of time in which I'm talking. By being able to record this movement, you will of course be able to reproduce this movement and, in other words, reproduce the sound of my voice. In fact, this is where the story ends for analog recording devices, like tapes or vinyl, because, well, they basically store exactly that, an analog representation of how the air actually moves over time. But let's say now we want to do something a little bit more complicated. We want to actually grab the sound information and store it digitally. That is, of course, on a computer or any other electronic device. Because of the way these storage devices store information, we cannot simply take a continuous piece of data, like a sound wave, and expect, to save that wave verbatim. There's just no way. We have to actually discretize it first and then save these discrete samples. And in fact, I've just actually used the word that describes the process, and that is sampling. The whole idea is this. When you have a waveform that looks like this, well, what I can do is I can say, all right, at this point of time, this is the amount of displacement, in the vertical axis, and then I'll move forward by a little step of time, and I'll record that down again. So instead of somehow storing the entire original wave, what I'm storing is just the amplitude of the wave at a particular time interval. So essentially, you can think of it as, instead of a line, I essentially have a list of points. Of course, since this is now a set of discretized samples, I can easily save all of these, right? Every position is just a number. I can, of course, reconstruct the wave by laying them out and connecting them together. So there you go. That is how we actually solve the problem of, how do we actually save a continuous wave into a media that only stores discretized information. Basically, just take samples, and that gives us a discretized representation of the continuous information. So that's great, right? We've solved everything. Well, not exactly, because the concept of sampling still gives us some issues. Now, before we continue, let's take a very quick detour to look at the concept of frequency. I'm going to be using this term quite a lot, so yeah, let's try to make sure we're on the same page with regard to its definition. What I have here is a sine wave. And essentially, in this sine wave, it's basically one segment that is repeated over and over and over again. The frequency of this wave refers to how many times this single segment repeats itself per second. So if I were to say a 440 hertz sine wave, then you basically imagine a wave that looks like this, repeated 440 times over per second. Of course, this does not just apply to a sine wave. Basically, almost all sound is essentially made up of one short segment that repeats over. So yeah, you can basically say almost any sound has a frequency. And, well, you can express it in hertz. So just a very quick summary of the concept of frequency. Let's now move on. Now, take for example this. We have a wave that looks like this. Right, it's basically a sine wave and it is pretty high frequency. Now, what I'm going to do is I'm going to try and sample it. Don't forget that when we are performing sampling, The sampling interval, that is the distance between each one of these points, is arbitrarily determined by us. Of course, there are certain ways for us to decide, what sampling rate we should use. And in fact, this is something I will cover in this particular video. So yeah, just hang on to that thought. Let's just take a look at this kind of contrived example. All right, so I have a sine wave, and now let's say I want to sample it at this particular interval. So taking samples, I get something that looks like this. Now, when I actually use these samples to reconstruct the wave, you notice a problem. The wave we get back looks nothing like the original wave that we've tried to sample. This is a problem called aliasing. And a simple way to describe this would be if I were to sample any signal at too low a sampling frequency, I'm unable to accurately represent that frequency, and I end up getting a lower frequency instead. While we've done this entire video in terms of sound, aliasing can happen anytime sampling is used. For example, image rendering. See how the checkerboard pattern over here appears to sort of merge together? Well, that's aliasing. So what we're going to do now is we're going to move on to the next important concept, and that is, how do we avoid aliasing? Now, I'm going to quite grossly oversimplify this concept, but hopefully I can still carry through, the core meaning behind it. Essentially, the idea behind this theorem is if there is a maximum frequency that I want to hear, that is a maximum frequency that I don't want to, get aliased and destroyed, this theorem tells us what sampling frequency we should use to guarantee that. The Nyquist theorem simply says this: the sampling rate should be double that of the maximum frequency you want to represent without aliasing. To be very exact, if your sampling rate is 2B, then all frequencies less than B will not be aliased. Notice how we cannot guarantee that for frequencies that are exactly half the sampling rate. Let's try and make this more clear with an example. Let's go back to the sine wave we've seen previously, and let's first try and see why there's a problem with sampling at exactly double the frequency. We begin by identifying one cycle of the wave. To sample at exactly double the frequency of this wave, we'll need to take two samples in this interval. Watch what happens when I try to do that. All the samples land at exactly 0, and we end up reproducing a signal that is entirely silent. And that's why I have to emphasize that for a sampling rate of 2B, you only get to keep frequencies less than B. What this means is, for this particular wave, we have to sample at a rate of slightly more than twice every cycle. So here's my attempt at very roughly doing that. As you can see, the samples are now capable of giving us a fair representation of the original signal. And there you go. That is the Nyquist theorem, and essentially that is how you work around the issue of aliasing when it comes to sampling a signal. Of course, you might hear these two terms that may be slightly confusing, so right before we end off, let us actually define these two terms so that, when you see them in literature, you know what's going on. These two terms are Nyquist rate and Nyquist frequency. And, they might sound a little bit similar, but they actually mean completely different things. Nyquist rate refers to the sampling rates you need to use to prevent aliasing, whereas Nyquist frequency refers to the maximum frequency you can represent given a particular sampling rate. The way I like to tell these two apart, because they can get quite confusing, is that Nyquist rate uses the same term as sampling rate, and therefore one is referring to the other. Hopefully this helps you in telling the two apart a little bit better. Anyway, that's basically all there is for this particular episode. I know it's run a little bit long, but hopefully this gives you a very clear idea of, the whole concept of sampling and what can happen as a result of sampling, and that is the problem of aliasing. And finally, how do we actually fix this problem? By sampling at a correct rate. That's all there is for this particular episode. I hope you learned something today, but until next time, you're watching 0612 TV. Thank you very much for watching. If you like this video, consider checking out the rest of my work online.
Okay, how to reproduce the analog signal and converting to jitter. That's what we will be going over. Sampling rate. How many bits are required? How often should we sample? Or what it means by how often do we need to read the analog signal? Okay, so this one will summarize for you what we will be doing. Analog signal is to be transmitted in digital form. Outline briefly the principle involved in analog to digital conversion of the signal and its transmission. Right? Conversion from analog to digital, and then you transmit it. Signal is sample first. Right? Whatever wave you have, your speech, you have to sample at regular interval. Signal voltage converted to jitter. After a sample, you got numbers that varies with time. Each different number at different time, then you have to convert it to binary or digital number. Then you transmit as a series or groups of pulse. Remember, we are having a number, and that number is binary. It's like 1, 0, 0, 1, 0, and then you have to transmit this group. Pulse could be in infrared, pulses in optic fiber. Right? We can use infrared pulse in optic fiber at twice the maximum frequency. Right? We will come into that term in a while. Use parallel to series converter if you want to go for long distance communication. Right? That will be part 2 of this lecture. Okay, let's look at that's the original analog signal. Right? We should be able to read what's the frequency. There is a period there. Right? There's a period there about 1000 microsecond. So we convert that is about 1 kilohertz. So the first step is to sample it at regular interval. Means you read the graph at regular interval. So we read that, we get 12 at 125 at 125 at 250 at regular interval, we get 12 volt, 14 volt, 12 volt. Right? So in this case, you should be able to read the sampling period is 125 microsecond. And you should be able to calculate the sampling frequency or sampling rate. Right? 1 over the period, change that to SI unit, 10 to the power minus 6, and you use calculator, we get 8 kilohertz. Right? This is 1 kilohertz signal, we sample at 8 kilohertz. And then we transmit as binary code of 4 bits. That is written as 110, 14 is 1110. So that's our first step. Signal is sampled at regular interval. At a particular time, we read the graph. That's what we get. Then we convert the signal voltage converted to digital number. Right? Remember when you send it as digital, so we convert it to binary number. Then it is transmitted as series of pulses. Right? That's a series of pulses. Right? So there's your pulses. It's just an example of pulses. There's your original signal. Right? We sample it at regular interval and convert it to, we have a special IC that will do it for us. This pulse we send analog, we just send it in and then come out here. It will sample for us at regular interval. Signal is transmitted as a series of group of pulses. For example, there's the first one, and the next one, and then this is called analog to digital converter. So at the other end, on the receiving side, we must have digital to analog converter, DAC. One wire for each bit. There are 4 bits, so we need 4 wires. And join it to the digital to analog converter. We use 1 wire less, we lose all our data. So we have to have exactly 4 wires. Then it convert forwards from digital to analog. That's what we get. Okay? Quite similar, but not exactly the same. Right? Go further. Using modern integrated circuit is now easy to convert an analog signal to digital signal. Right? Basically, it's just easy. Just use an IC ready for us. Right? So this IC is described as ADC or analog to digital converter. Digital signal can be converted back into the corresponding analog signal by digital to analog converter, DAC. Okay, so if that ADC got 2, 4, 6, 8, then that also must have 8 wires, 8 terminal for wires, DAC, to receive the original analog back. ADC convert each sample of the analog information into code of n bits. 1 0 0 0 1 3, sorry, not 3 1 0 1 1 1 1, like that. That's your binary number, or we call it digital. The n bit code are transmitted in n parallel wires. In this case, we got 8 binary bit, then we got 8 wires, 8 parallel wires. So n code are transmitted in parallel along n wires, one sample after another. That sample is sample it, a number in binary, send. After that, another sample that we have sample in binary, send. To a matching n-bit digital analog voltage from the coming code. So whatever you receive binary here will reach here and convert back. So because the ADC is only 4-bit, there can be only, remember, it can be 0, 1, the first digit, the second digit, 0, 1 also. So it means that you got 2 choice. Right? So altogether, you can have 2 to the power 4 possible outcome, or words that can be produced. Right? We call that word. The 4-bit is called the word length. Word length is reduced 4-bit, so 4 word length is 4 bit. So in this case, it's 0. DAC is 0. Right? 0, 0, 1 is 1. So 0, 0, 1, 0, the digital to analog converter will convert to 2. And so on. And 1, 1, 1, 1, the 4, 1 there is converted to 15 for us. So word length equals the number of bits in the word. Here the word length is 4 only. 4 bit, word length 4. Analog signal from, right? There's an analog signal that we have recovered using our DAC. This produces a step analog voltage from the incoming code. Remember, we are receiving code, and then we convert it, and then we get analog. The output is often called staircase approximation to the original analog signal. It's like climbing a stairs. That's why we call it staircase to the original analog signal. Not exactly the same, but it's quite similar. Right? That's called the step height. It's called the depth or width of step. Okay, so that's our original signal. That's the recover one. Right? So we can see that there are similarity, but there are also differences. That maximum one we miss out. That one, okay, very similar. That one is captured almost there, but not the correct value. So one, how to reduce that? Increase the number of bits in the jitter number at each sampling so that the tap height is reduced. If you want to reduce that, increase the number of bits. And depth, increase the sampling frequency. Sample more often. So you reduce the depth or the width of the step is reduced. So modern, we use 12-bit converter. For example, if ADC and DAC are 12-bit converter, then the number of possible outcome is 2 to the power 12. And the step height, if you use our example, 14 volt is the largest value, then you divide by that, then we can read up to 3.4 millivolt. 14.4 volt. 14 volt is our maximum value that we send. So you can see that we can read to quite small, right? Rather than just 14. Thus, the word length is important in determining the quality of the final output in the digital transmission. Number of bits determine the step height. These differences. We also sample more often. We decrease the step width. Right? We take more reading so that we don't miss out some points there that may be lower or too high. Pulse transmitted at twice the maximum frequency. Sampling rate or sampling frequency. The ability of this system to transmit and recover the original analog information is dependent on the sampling rate or sampling frequency relative to the information frequency. And we'll illustrate in a while. A lower sampling frequency means less information can be gathered from the analog signal. Means we will find later on if our sampling frequency is too low, our final information that we get is completely different from the original information. Let's go a simple one. This is period is 2 milliseconds. Convert it. Frequency is 500 Hz. What happens if we sample at 500 Hz? 500 Hz, remember we sample at 2 milliseconds. And you are just reading point there, that's all. All that. So it means that when we finally receive the information, it will just be a horizontal line. Right? You can see the information original and the final information that we receive is completely different. Output is horizontal line, completely different from the original input. Nyquist frequency. Right? The 1924 Dutch mathematician Harry Nyquist showed that to recover an information, the signal from a series of samples, the sampling frequency must be twice the maximum frequency in the information. So if the maximum frequency, if S max, then the sampling rate or sampling frequency must be 2 times your 2F max. This is known as the sampling theorem, and the frequency of 2F max is known as the Nyquist frequency. For recovery of information, Nyquist frequency or sampling frequency is 2F max. F max is the maximum frequency of the information. part 2, we will carry on from here. And then we'll do some worksheet there, try some example. That's our next topic. Right? We're looking at transmitting signal in digital form and recovering the digital signal. So you want my video or you want my notes, you can go to A-Level A2 right, and Facebook and get my notes, PowerPoint, and the video we deposit there. Or you want past year paper from 2001 to 2010, topic by topic, to practice whether I understand what is going on here. They can download from this part there, Facebook also. Or you don't have a Facebook account, you can go to YouTube, look under my name, and look under the level you want. Thank you. That's the end of the lesson for today.